Geez, Charlie, how are we ever going to figure anything out with these things in our way?
Well, Ed, they're all we've got right now, so we better learn to live with them.
In the last program, we graphed y equals sine x, using both degrees and radians. We used a table of angles and their sine values. Then we plotted the x and y values on a Cartesian plane with the angles on the x-axis and the sines of the angles on the y-axis, and produced the sine curve. Substituting the corresponding radian values on the x-axis, we produced exactly the same curve. These curves are called waveforms and have two fundamental properties, amplitude and period. The amplitude of a wave is 1/2 the distance between the highest and lowest peak. In this case, a peak-to-peak distance from +1 to -1 is 2 units. Divided by 2, the amplitude is 1. This curve is y equals sine x, but how would we describe this new sine curve? We don't know its equation, but we can see its amplitude is 2 units. To write an equation for the new curve, we must double the amplitude of y equals sine x. So we multiply sine x by 2. Y equals 2 sine x is the equation for this curve. Y equals 3 sine x is the equation for this curve. So, if we wanted to write a general equation for sine waves of various amplitudes, it would be y equals a sine x, where a can take on many values. Notice that when we change the amplitude, the curve still crosses the x-axis at the same points. Now let's look at another property of sine waves, the period. The period is the measure of the horizontal length of one complete wave, sometimes called a cycle. This wave has a period of 2 pi radians. If we continue plotting, the wave simply repeats itself over and over. Let's look at another curve. It crosses the x-axis at pi over 2 and completes one cycle here, so it has a period of pi radians. It has the same amplitude as y equals sine x, but its period is shorter. With a table, we can see the differences between y equals sine x and the new curve. A calculator gives us the values of sine x. The new curve crosses the x-axis at pi over 2. This means the y-coordinate is 0 at this point. When x is pi over 4, the y value is 1. Look at the bottom row of the table. The new curve seems to have incorrect sine values. The sine of pi over 2 is 1, not 0. It's the sine of pi that is 0. And the sine of pi over 4 isn't 1, it's 0.71. Now look at the relationship of the angles. Pi over 2 is twice pi over 4. and pi is twice pi over 2. So, the sine values we observe for the new curve are really the sine values of twice the given angle. Let's double the angle in the equation and see what happens. This makes it y equals sine 2x. It's this doubling of the angle that causes the period to be shorter. Notice the difference from before. We are doubling the angle and then finding the sine value. Earlier, when we were changing the amplitude, we found the sine value of the given angle and then doubled the result. The equation works for any x value. When x equals pi over 4, we first double the x value, making pi over 2. The sine of pi over 2 is 1, and we use the 1 for pi over 4. We can fill in the rest of the table for y equals sine 2x. 2 times 0 is 0, and the sine of 0 is 0. We have values for pi over 4 and pi over 2. Let's try the next one. Twice 3 pi over 4 is 3 pi over 2, and its sine value is minus 1. Twice pi is 2 pi, and its sine value is 0. So, by introducing a factor in front of the angle, we can change the period of the sine wave. Now let's look at y equals sine 1/2 x. We can make a table and find sine values for 1/2 x. When we plot, the curve rises up to a maximum of 1 at pi radians. At 2 pi, we find the sine of 1/2 x to be 0, and because y equals 0, the curve must cross the x-axis at this point. The curve y equals sine 1/2 x has a longer period than y equals sine x. It's 4 pi. Let's see what we've found out about sine waves. We started with the equation y equals sine x. To change the amplitude, we introduce a factor. Let's call it a. It can be any value. In this case, the amplitude is 3. To change the period, we need another factor. Let's call it k. So there it is. Y equals a sine kx is the general equation for a sine wave, with a controlling the amplitude and k the period.
Listen, Ed, if we aim our antenna properly, we might be able to pick up one of those things.
We've got one, Charlie. It's on the screen.
That's great, Ed. Now what do we do?